class, we did a really nice little chart here on how to figure out the difference between bonds, which you're going to see right here, and molecules when we're trying to figure stuff out. They are so different. And what we'll try to do here is give you a really clear idea as to what goes with what. And let's just get rid of those right now and go on with what I actually did in class. First of all, I asked my students to focus on the bonds. Oops. So I'm going to focus on this bond right now. If I can just get this silly pen to right. There we go. We'll focus on this bond, which of course is the same as the bond over here. Okay? So that we don't have a mass confusion here, I'm going to just focus though on the one bond. And let's go ahead and see whether that bond is polar or nonpolar. And I'm going to put up the reason first. And the reason for this is going to be because we have two different atoms. Because we have two different atoms, that bond is going to be polar. And the thing that the students in class today seemed to find most troublesome was separating a bond or a pair of atoms that's put together with a bond from the entire molecule. So now let's get rid of this bond thing and let's look at the entire molecule for the next column. So now we're looking at this whole thing. So over here on polarity, because beryllium has no unshared pairs on the central atom, or no lone pairs, depending on how you want to state it, this guy is a nonpolar molecule, but he has polar bonds within the molecule. And so, you remember what I just said for the reason? That's right. The reason is because there are no lone pairs on the central atom. So, let's take a look at molecule number 2. Okay, in molecule number 2, again, we will focus on just one of the bonding pairs, or bonding pair of atoms. And the bonding pair of atoms has a bonding pair, only one bond, between that oxygen and fluorine there. And so what we want to do now is we want to figure out, is the bond polar? And I would like you to stop the tape now, or stop the recording, and see if you can figure that out. Now hopefully you stopped and tried it for yourself, and if you have the actual notebook file that I'm doing this in, you could have done this with me and actually figured these things out as well. At any rate, for this particular bond that we're looking at, this guy is polar. And as you hopefully guessed, it is because the two atoms involved in that bond are different atoms. Now, let's go over to the molecule and see if the molecule is polar. Well, this guy is, and let's see if you can figure out on your own why it's polar. Look down at my list of reasons and choose one, and I'm going to wait for you. Stop the recording. I hope you did that and you found out on your own that that particular molecule, now we're looking at a molecule instead of just the bond, which is what I just had circled earlier. And so this is actually the whole thing that we're talking about now. The whole thing is a polar structure. And that is because we have lone pairs on that central atom, which in this case is oxygen. You'll notice in the last one we didn't have any lone pairs on the beryllium. Okay, so that guy made a nonpolar molecule. By the way, another reason for this guy being nonpolar is because, and it's a very important reason, the molecule is symmetrical. Symmetrical means that the atoms on either side of the central atom are the same. Now, in this guy, it was also symmetrical. Okay, one we just did. This is also symmetrical. But because there's lone pairs, notice this guy had lone pairs, this guy had no lone pairs. So because there's lone pairs on that central atom, he winds up being polar. Okay, the last example on my little chart here is carbon trioxide, the ion, CO3, also called the carbonate ion, is a common name. And as we look at the Lewis structure, we could look at either this bonding pair, or we could also look at this bonding pair. Oops, not that. Yeah, I did that a little bit wrong. All right, let's look at, okay, let's get that back. All right, we could look at this one. In both cases, we would have the same result. In other words, the polarity of the bond would not be an issue. It's definitely going to be polar. And for the same reason as all the rest of them, it's going to be polar because there are different atoms on each side of the bond. Now, as we change from just looking at a bond to looking at the entire molecule, we see that we have no unshared pairs on the central atom. Without unshared pairs on the central atom, this guy becomes a nonpolar molecule. So we say no lone pairs, the same as saying no unshared pairs on the central atom. And we have another reason. Can you figure that out on your own? Stop the recording for just a minute and say to yourself what that is. Yes, you're right. Symmetrical. Okay? So this little guy is symmetrical, and that makes him nonpolar. And let's go down the list now and look from atom to or molecule to molecule. Okay, let's start with the beryllium difluoride, the guy on the first line. And as we look at beryllium difluoride, we're first of all concentrating on the bonds, and let's go all the way down on the bonds, and let's look at bonds for each of our molecules. And let's do this one this time. There we go. Okay. Now on the top, we have a polar bond, and the reason it's polar is because of the beryllium and fluorine being different atoms. And then we go down one to the difluorine oxide, and the difluorine oxide has a polar bond for the same reason. And as we go down to our carbonate ion, also could be called in the systematic name as trifluoride, trioxide. I'll get it right. Carbon trioxide. The carbon trioxide is also a polar bond, and for the same reason, because it has different atoms. Now let's review the molecules themselves. So we'll circle the whole molecule this time as we talk about the last column where we're talking about molecules themselves. Okay, and I've circled the molecules. Let's do the beryllium difluoride first. Nonpolar, again, because of no lone pairs, and the fact that the fluorine on the left and the fluorine on the right, you have the same atom. By the way, let's take a little side trip here, and let's look at what happens when we put beryllium, and we'll take fluorine on the left like we had before, and we're going to replace him with bromide. Here, Br. on the right. Now they both have the same number of valence electrons, so the Lewis structure is absolutely the same. But in this case, we have what's called a dipole. The dipole happens because we have electrons being shoved or pulled, actually, more towards the fluorine than to the bromine. The bromine is on the right, and he's kind of losing some control of the electrons. They're being moved towards the fluorine, and he becomes partially positive. This is the lowercase Greek letter delta. And that indicates, because there's a plus there, that he's become a little bit positive. And then on the other end, a negative, because this guy has become partially negative, because fluorine wants electrons, pulls them more than does the bromine or the bromine. And so we have a dipole here, and that makes this guy, let's put up the stuff for him. He is going to be polar, and the reason he's going to be polar is because he has, as you can see here, two different kinds of atoms around the central atom. So that one would say that he is not symmetrical. We don't say different atoms like this guy would say, because different atoms is applying to just the single pair of atoms on one side of the molecule. Like that would be different atoms. And that would be referring to the bond. But when we say that the molecule, we're in the molecule column over here, because the molecule is polar because it's not symmetrical, meaning that the fluorine and the bromine are actually different atoms, and that makes it asymmetrical or not symmetrical. And that should be a big help for you. Let's go back and finish off the molecule summary, and let's go to the difluorine oxide, which is right here. And now let's go and figure him out on the molecule side. He is polar because he has lone pairs, and those lone pairs are right here. Okay, lone pairs on the central atom, which makes him a polar molecule. And he also has to have two fluorines. They must be the same, or they will not be symmetrical. And actually, if it were not symmetrical, it wouldn't matter. He'd still be polar. Okay? In the carbon trioxide, or the carbonate ion, that baby is going to be nonpolar. Okay, now we're talking about this row right here. And it will be nonpolar because there's no lone pairs on the central atom, and it is symmetrical. Now, watch what happens if we make this asymmetrical. Let's first of all do some erasing. Okay, our last molecule will show you the difference between the carbon trioxide or the carbonate ion, and I forgot to put my brackets around this guy. He's still an ion. As long as I take sulfur, who's in the same column as oxygen, they're in the same group, we will have the same number of valence electrons, and the Lewis structure will look the same. So let's go ahead and work this guy out. Is he still going to have polar bonds? Absolutely, because at every bond we have different kinds of atoms. So whether we're looking at this particular bond, I should have included carbon in that, or this particular bond, and let's erase, or if we're talking about this particular bond, it really wouldn't matter. Every single one of them is a polar bond, and that is for the same reason that we had polar bonds before, and that's because the atoms are different. Now let's do the last one on the right here for the molecule, however, and let's get rid of this little guy. And in the molecule, we're going to have a polar molecule this time. Polar molecule. And the reason is because we have this sulfur here, which is different from the other two atoms that are around the central atom, which are oxygens. That sets up a dipole within the molecule and makes the whole molecule polar. And so we have still have no lone pairs around the central atom, but that is not what's going to make the difference. The difference is that it is no longer symmetrical. No longer symmetrical. And so because of that, the asymmetry with that sulfur there on the right side, like I just showed you, it's going to change this guy from a nonpolar, which is what it looked like here, to a polar. And in the nonpolar, we have perfect symmetry, no unshared pairs, nor no lone pairs, and you have nonpolar. But we got to polar as soon as we changed the symmetry. So that's your summary of how this stuff works. And we'll have one more little thing to tell you. All right, I've carried forward the last little model we were looking at. And so let's look at it one more time and compare and see what we're talking about for bond versus molecules. Let me get this guy right in the middle for us. And let's watch and see how this works. For bonds, we're talking about either this. I'm doing it in blue because I've written bond in blue. Or this. Oops, that really moved on me. Here we go. Let's try it again. All right. Or this. Oh, doggone thing. Just doesn't want to draw right the first time. Oops, here we go. The whole thing here. There it is. Okay, those are what we would be talking about when we're talking about bond polarity. With molecule polarity, on the other hand, we are talking about the whole banana. Okay, the whole Lewis structure. Okay, the whole structure of the molecule being polar or nonpolar. I hope this has helped.